thank you. Yeah, also thanks to the organizers for this very nice conference and program. Yeah, so I want to talk a bit about waveforms. And in the title, in the program, it also said from compact binaries. So just 10 minutes ago, I got the question what compact binary is. So that's just a binary system composed of compact stars, right? So either black holes or neutron stars, or sometimes one also calls a white dwarfs a compact star. Yeah. As we heard already in the morning, a binary of two such compact stars is producing gravitational waves, which can be measured. So the reason why we need waveforms and good waveform models is because we have to run the data analysis on the data that is measured by the detectors, right? And one quantity that one really wants to compute is the posterior probability, say, to find some waveform H in the measured data. So this symbol means the probability of H given that the data D was measured, and probably given some other hypotheses that enter the analysis or the measurement. So this is a quantity that one is really interested in. So this gives you, say, the probability of the waveform, finding a waveform with given masses and spins in the data. You can compute this, as we've seen in the morning, by applying Bayes' theorem and reducing it to a quantity that you can actually compute, namely the likelihood, which is basically your noise model. So you express the noise in terms of data minus waveform. So if you have the noise model, the probability to find a given noise realization, and you know you have a waveform model, you can compute the likelihood, and from the likelihood you can compute this posterior probability. So that's not even talking about things like detection, which is a whole other problem. But if you just want to infer the parameters of a binary, you need a good waveform model, right? And more precisely, what goes in here is a frequency domain waveform. The reason for that is because the noise model really works in frequency domain, right? So you know the power spectral density of the detector in frequency domain. So you compute your probability of a given noise realization in frequency domain. And so it's most useful to have a waveform also in frequency domain. Which brings me basically to the first, say, distinction between two classes of waveform models, which is time domain versus frequency domain waveform models. So you have waveforms in time domain, and with waveform, now more precisely, I mean the plus polarization of the gravitational wave plus I times the cross polarization. And in time domain, say if we plot the real part of the waveform over time, looks a bit like this. So you have a sinusoid with some frequency, and then the frequency and the amplitude grow over time until the amplitude reaches some maximum, and then you have a ring down of the final black hole. So that's how that looks. And here we can basically separate the waveform into different pieces, more or less. So we have some kind of ring down over here. And we have the in spiral part over here. Right? So in the spiral part, the two black holes move towards each other. Then at some point, there's a merger, which say is here. Whoops. I guess you cannot read this very well. I try to write bigger. So here there's some merger, and then the final black hole rings down. So that's one way of separating the waveform into pieces. There's another way by, so to say, looking at the methods which you can use to predict these different stages. In the very early in spiral, say on this side, you can use analytical methods. And here on the right side, so to say, when the two black holes come very close and the field is strong, velocities are large, you have to use numerical relativity. Oops. Right. So that's more or less how it looks. So you have an in-spiral merger ring down waveform. You really usually need the full thing, and you need analytical and numerical methods to compute it. You can also use some methods just to compute the ring down, right? But numerical relativity usually also gives you that. So yeah, once you're able to run the simulations, you get the whole last bit over here. Now in frequency domain, it looks like the following. So usually one plots that on a log-log scale. And let me just show you the amplitude, not the phase. And so we've also seen a plot like this in the morning that looks a bit like this, right? And here again, we have some kind of in spiral regime up to here. Then there's some merger regime, and there's this last bit, which is the ring down. Yeah, so that's how it looks in frequency domain. And of course, you can always go between the two by a Fourier transform. So in principle, it doesn't really matter whether you compute a time domain or a frequency domain waveform. It's just that the data analysis already is quite challenging enough. So if you can skip doing a Fourier transform to get to the frequency domain waveform, you often save a bit of computational time. So that's why often the frequency domain waveform models are a little bit quicker and better adapted to data analysis. Yeah?
Can you give us the early history of the time domain waveform? Why does that affect the frequency domain waveform?
What do you mean?
Something? I mean, are you just taking the Fourier transform of the signal on the left?
No. I mean, it continues.
Just goes on forever, and it doesn't affect what happened in the detector in the last few seconds. And you only see, when you get in the data stream the time domain.
Yeah.
So won't the Fourier transform that left?
Yeah.
Depends on what you assume in the past?
Yeah, so that's a tricky question, yes. So usually when you go to the infinite past, the waveform gets a bit more monochromatic on average because the change in frequency is driven by radiation reaction, which is, so to say, it's a slower time scale than the orbital motion, right? So in the very infinite past, basically, you almost don't see any change in the frequency. So at very early times, the very early times are almost monochromatic and don't contribute very much to high frequencies. But still, I mean, of course. Yeah. Yeah. But of course, you're right. I mean, what is a good point still is that, I mean, here the merger, it's one point, right? It's when the two bodies touch. But in frequency domain, maybe one cannot so easily say where the merger is, right? It's not at a specific frequency, it's at a specific point in time. So here, what you have is you can still have some numerical, analytical predictions for the low frequencies. And of course, you can try to get the high frequencies from numerical relativity, but it's a bit tricky to do that, right? You really should perhaps first complete the numerical relativity waveform with an analytical time domain waveform, then do the Fourier transform, and then, so to say, build your waveform model. Yeah?
Just comment, you said the merger is where the objects touch. That's kind of a really stringent definition of merger that maybe is not universally.
Yeah, that could be how would you define it?
We might need to repeat the
Oh yes, that's a good point. Yes, sorry. Yeah, I can also try to repeat the questions. Yes. Yeah. So the comment was that, so to say, defining the merger as a time where the two bodies touch is maybe a bit too stringent. So I was just asking, so to say, how you would define it. If you want to take the mic.
I generally go with a functional definition of after whatever expansion treatment you do in the inspiral breaks down, but before it's acting as a sum of quasi-normal modes, which is a good bit more than that really narrow interval you have there.
Yeah. So what do you mean by when the inspiral breaks down?
Any perturbative treatment that you might.
Yeah, but where is that? I mean that.
Right. That's what I'm saying. There's not a rigorous one definition to pick, but all of them break down. If they're not calibrated to numerical relativity, right? All of them break down, a cycle and a half, 2 cycles before.
Well, I mean, if you really want to get very accurate waveform, I would say the postNewtonian treatment breaks down many cycles before that, right?
Okay.
But I mean, it's then
even more so then, right?
Yeah, but then you have a merger of 20 cycles, so that's also weird, right?
Anyway, just throwing it out there that there.
Yeah,
that's
but
not
you're
the
right.
Universal definition.
Yeah, that is true. That is true. Yeah.
Would you like the microphones?
So one thing is the merger process, which of course you can't define it because it's something that happens. But usually in the technical literature, I mean, probably what he was referring to, the peak of the two mode, which is something that is well defined. This is what is used in the literature, often technical literature that talk about these things. So one has always, from the context, understand which one of the two the paper is, but it's easy to get it.
I think that's not what's used in any numerical representation literature at all.
It is.
Yeah. So yeah. So the comment. Yeah. Indeed. Yeah. So one often defines the merger basically as a point of maximum amplitude, also because even numerical relativity, it's not so easy to say when the bodies touch, right? So yeah, exactly. Yeah. So not even of the waveform, but of the two modes specifically. Right. Okay. Yeah. Okay. So now let me maybe give you some terminology of how those waveform models are called. So I've been mostly working on time domain waveform models, like Sebastiano, you too, or did you also work on phenomenon models? Okay, everything good. So here on this side, we have the so-called TUV some S models, for instance, and the models by our group usually start with S, E, O, B, NR. And then there's some version number, so we are approaching version 5 of the waveform model now. There's also a more recent approach, which is called IMR phenom T, which is, so to say, it's an approach more from the group, let's say, who were doing frequency domain waveform models, which usually was called IMR for inspiral merger ring down. Phenom because it's, because it's partly a bit phenomenological, let's say, right? So you kind of use analytical results at low frequencies and then maybe some kind of fit, roughly speaking, for the last part. But they also tried to construct time domain waveform models recently just to cross-check results. But for a longer time, also these two waveform models had been around. There's also here, there's a waveform model that's still sometimes useful, which is called Taylor F2. So that is based just on analytical results. And for low masses like binary neutron stars, that can still be used because the merger is not in the band of the detector currently. But at some point, I guess this will have to retire. Now, I will mostly discuss this family of waveforms now. And here the EUB basically stands for effective one body. Oops. So that's this EUB here. And I would try, I don't know if I will manage, but there are 3 building blocks in these waveform models, which are the following. So the building blocks here are the conservative dynamics. Which usually is described via a Hamiltonian function. Then, on top of the conservative dynamics, one then models the radiation reaction. Right? And these two together basically give you the trajectories of the 2 black holes or neutron stars. And having the trajectories, so to say, one can compute the multiple moments of the binary system, and from that, the gravitational wave or the gravitational wave modes. Yeah? So the waveform usually is computed in a kind of harmonic decompositions. So it's related to a spherical harmonic decomposition, roughly speaking, which gives you the angular dependence of the waveforms. And one computes each of these modes separately from the trajectories over here. Yeah, so that's the usual approach, how it works. So, yeah, are there any questions on this part? The S, I think, is spin usually.
The question was, what does the S in SCOB stand for?
Yeah, so, great. Then I'll tell you a bit about the conservative dynamics and the Hamiltonian, which to me always is the nicest part of the story. So if I don't get to all the bits, the other bits, then it's also good. All right. So yes, for the Hamiltonian, yeah, that's a very nice idea for how to construct it and how to improve the analytic predictions with the Hamiltonian. And the idea is coming from Newtonian physics, basically. So it's coming from the treatment of Newtonian binaries. And maybe everyone recalls that in Newtonian physics, if you have a binary system, say, okay, let me draw it as a scattering, in fact, like this. So here there's body 1 with mass m1 and momentum p1 coming in. And here's the body 2 with mass m2 and momentum p2 going this way. Then, I mean, there's a different way of treating the system by mapping it, so to say, to a one-body motion, right? Where basically you have the total mass over here, which doesn't move, but is just sitting as an external potential there. And you have an effective body scattering in that space-time with the momentum small p and the mass mu, which is just the reduced mass. So it's m1 times m2 divided by the total mass, right? Now, here, one could also add, say, a center of mass motion. So let me just put it here so we have it defined. I will call that big P. I put some foot under it, so that's a big P. And let me also, for later convenience, put here the radial separation vector, small r. And the mass ratio in the effective picture, which is also called the symmetric mass ratio, because it's symmetric under flipping mass 1 and mass 2. So in Newtonian physics, you can basically map between these two pictures and these two descriptions of the motion. Now, we want to do something similar in relativistic physics. And that's difficult, and there's probably not a unique answer of how to do it, but I will show you one that works quite well. So a relativistic version looks like the following. You can write the Hamiltonian as the square root of the total mass square times 1 plus 2 times the symmetric mass ratio times an effective Hamiltonian HE, which I'll explain more in a bit, divided by the reduced mass minus 1. And over here, one could also still put the center of mass momentum square, like this. Okay, so I claim this is a good Hamiltonian to describe the binary system relativistically, which, so to say, makes the transition to the same variables as in the Newtonian case, right? Like total momentum of the system and the relative momentum, small p. And yeah, the point is that this HE here, you want that it depends only on the relative phase space variables, small r relative separation and relative momentum p. And this then usually is called the effective Hamiltonian. All right, and to zeroth order, say in the scattering scenario, zeroth order would mean both guys just move on a straight line. To zeroth order, so when we just have two straight lines, this effective Hamiltonian is another square root of mu square plus the small p square, right? So that's the relative momentum. Now, this is rather non-trivial, I would say, because on the left-hand side, say, when you have two bodies moving on a straight line, you would have two Hamiltonians of this kind, with here m1 p1 and m2 p2, which are added together. So you have a sum of two square roots. So now the claim is that you can do a canonical transformation that transforms it into this, where you have one square root, and then you have another HE in here, which is another square root, right? But indeed, this works. One way maybe to see why this makes sense is if you compare to the energy in the center of mass system, you can work out a formula which looks like this. Yeah, so this was pointed out in the paper by Damgaard and Van Hoff, that basically this so-called energy map that is used in the EB model in the scattering scenario is just this formula for the center of mass energy depending on the relative gamma factor of the scattering bodies. So in this picture, basically, one can see this as some kind of basic kinematics. Whoops. In the sense that you compare the two formulas, then HE is just mu times the gamma factor. Right, which somehow makes sense. And here, yeah, I guess you could also add here the center of mass motion by putting the p square under the square root over here. Now, the trick is that you take this, so to say, mapping of the binary system to this new system where you separate center of mass motion and relative motion. You take that, and now you basically deform this effective Hamiltonian, or the Hamiltonian of the relative variables. And what you do is, yeah, in the effective form body model, yeah. So first of all, you set the total momentum to 0. That is to say, that's an approximation, yeah. So you discard half of the phase space variables. You don't consider the center of mass motion anymore. You just have the relative motion. So that it reduces your dynamical variables by 2, which is nice. One good question at which point this might break down, yeah?
I was just going to ask, why is that an approximation? Is it because the center of mass momentum is not conserved?
Yeah, so in the conservative sector, it's fine. It's conserved, so it's exact. But once you add radiation reaction, it would be an approximation. So first you do that, and then you say HE now is a deformed test mass or test body Hamiltonian. Yeah, so in some senses, this could be considered as a test mass, test body Hamiltonian, just that there's no interaction, right? It's a free Hamiltonian, but you can substitute it by a Hamiltonian that describes the test body motion in the Schwarzschild spacetime. And the nice thing is that you know the spacetime non-perturbatively, and you know the test body Hamiltonian non-perturbatively, all the way into the strong field regime. So you start from that, you start from the test body Hamiltonian, and then you deform it to include post-Newtonian or PN interactions. Okay, and doing so really drastically simplifies your description of the conservative dynamics. And that's really amazing. So if you work in this so-called post-Newtonian approximation and say you work up to third post-Newtonian order, third order in the expansion, you get results in the papers which span, let's say, 3 or 4 pages. If you move towards this effective one-body description with the 2 nested square roots, and you take a Schwarzschild test body Hamiltonian and deform it a little bit, you can compress that very much. Yeah. So, I mean, I would claim I could write down the full 3PN Hamiltonian in maybe less than 1 or 2 minutes on the blackboard. Although, so to say, the original result is really long. I mean, it goes over pages and pages. So that is a very effective way of encoding the conservative dynamics. Right? So using these mappings between Hamiltonians and then starting with the non-perturbative test body Hamiltonian. And into that you add so-called post-Newtonian interactions. So now, yeah, I've used all these words like test body and PN and so on. Let me maybe briefly sketch what all of that is about. This goes, so to say, in the direction of which methods there are to compute the gravitational dynamics, right? And if you plot here on the y-axis the let me call it the minimal separation, or the periastron distance. And here on this axis, I want to plot the mass ratio, big M over mu. Then basically the so-called post-Newtonian approximation is valid over here. So that's this PN thing. And that's because the post-Newtonian approximation is an approximation in weak fields and slow motion, right? So you want the separation to be large. And the so-called post-Minkowskian or PM, it's basically in the same regime if one sets the eccentricity approximately to 0. So one has almost circular motion, then basically it doesn't matter whether you approximate in weak fields or in weak fields and slow motion, because once your field strength becomes bigger, also the velocity goes up. So there's only one expansion parameter, and these two approximations are basically the same for bound or almost circular orbits. Then there's numerical relativity. Or NR. And there's also the test body approximation, which maybe is around here. So the test body approximation is very good when the mass ratio becomes large. Yeah. And here one can also add further corrections like the self-force correction. So now the point is, what one tries to do is one starts with the test body Hamiltonian and tries to incorporate corrections from the post-Newtonian result, which is valid for any mass ratio, but where you cannot go into the strong field regime. And by combining these two results, one hopes to find a resummation, so to say, that extends all the way up to here. And this was first tried even before there was numerical relativity. And the waveforms that were predicted were actually quite okay, let's say. And today, basically, what people do is they also take the numerical relativity results to further improve the resummation of the Hamiltonian. Yeah, and maybe let me make a last plot, which extends a bit around this case here. So let's say we now don't restrict to eccentricity around 0, but eccentricity. But we can take the eccentricity to infinity. So we also include unbound motion and scattering. Then basically the NR regime of validity would be maybe around here. So as far as I know, it gets a bit harder to do the simulations when the eccentricity is very large, right? So if you keep the minimum distance fixed, if you want to have high eccentricity, you have to make the black holes very, very fast. So they move almost on a straight line motion. And then it becomes difficult to do the simulations. Now, the PN maybe would be around here. So similarly, when you make the eccentricity large at fixed minimal distance, you make the bodies very fast, and Pn is a slow motion approximation, so it has to break down. But the post-Minkowskian approximation, which is what one also computes with scattering amplitudes, doesn't have this restriction. So the expectation should be that it improves the waveform models when, so to say, going away from circular motion. So that's just a guess, but yeah, I just wonder if that is, so to say, or what your motivation would be to look at the post-Minkowskian approximations. For me, this is definitely something, and yeah, I think some people also would say that computing scattering amplitude at some points using on-shell method, for example, is more efficient at some point. In constructing integrands and so on, that could be another motivation, but yeah, that so to say is completing a bit more the view on the parameter space where which approximation is good. So it would be very good when moving to eccentric waveform models, try to incorporate post-Minkowskian into the EOB Hamiltonian, definitely. And also what is very interesting still is to go more in this direction by adding the self-force. Simply because this method can go all the way down into the strong field regime. So also pushing that to higher orders is very interesting. Yeah, so I would maybe stop here for further discussion. Thank you.
Thank you very much, Jan, for a very nice talk. And we're already 5 minutes into the discussion, but I let it go because there was discussion during the talk. So let's have 10 minutes of questions then. So let's start with Aaron.
Just hopefully a quick question.
Yeah.
The formalism for the EOB is, it seems, mostly in 3 dimensions with 3-dimensional vectors. Is there a particular convenience over that versus boosting it into a more 4-dimension, 4-vector language?
I would say no. It's actually a good point because all these Hamiltonians and mappings, I mean, there's maybe a better way to understand them in a 4-dimensional way. In a sense, you could say this thing here is just the minus the 0 component of a 4-vector.
Yeah.
When this is right, the 3-vector, and if you square the thing, you get something like a Marshall constraint, right? And you could, well, obviously here it's the same, right? So you could say this is minus P naught, right? So this is then just P mu equal minus mu square, right? So that can be very useful. It's yeah, so that could be done. I think it's often done this way because when you write it like this, yeah, you have to solve for P naught, and perhaps you could get some more nonlinear. Well, although this is, yeah, the problem is when you deform the Hamiltonian, you get further momentum dependence into the Marshall constraint because you say the metric can also depend on the momenta.
Oh, I see.
So then this could be more than quadratic order in the momenta. So it's then sometimes more useful to directly deform the Hamiltonian. Yeah.
Thank you.
Yeah.
Well, pick one.
Yeah, thanks for a nice talk, Jan. I have 2 questions. The first one is on your last graph there. Where would you put the test body self-force approximation?
Here?
No, the last one.
There. Yes. Oh, sorry. Yes. So this was supposed to be more for almost equal masses, right? So, but yeah, I mean, the test body approximation is always good when this is large, right? And then it should fill the whole thing, right? So in the test body Hamiltonian is valid for any eccentricity, basically. So it could be everywhere or it could be nowhere, depending on what the mass ratio is.
You need the 3rd dimension for that.
Yeah.
Yeah. And the second question is, so now you showed us how you arrive at your EOB, but how do you get the waveform now?
Yeah, right. So first of all, one would add radiation reaction forces. So this usually goes by writing down Hamilton's equation and just artificially writing forces on the right-hand side. Right? A Hamiltonian cannot so easily deliver for you dissipative forces. So you just put them by hand, and then you match them to the fluxes that you can compute. Right? And the fascinating thing is that somehow the angular momentum and energy flux, they uniquely seem to fix the radiation reaction forces up to gauge freedom. So this you can usually always do just by computing the fluxes. And the fluxes in turn you get from the waveform, let's say, or the waveform modes. Right? So if you know the waveform, you can compute the energy and angular momentum that's carried out of the system by the gravitational wave. Yeah. And yeah, so for the waveform modes, we then have formulas that depend on the trajectories, right? So the whole story is you take the Hamiltonian, you compute the trajectories, you plug it into the waveform modes, and then you can compute the energy and angular momentum of the gravitational waves also to get the radiation reaction forces. So it's all, it becomes quite complicated at that point. Yeah.
But this is then a multiple expansion with these trajectories.
The waveform mode expansion is a multiple expansion, yes. Yeah. And there it also gets a bit ugly because also there you want to have some resummation, right? So this Hamiltonian is a resummation in the end of post-Newtonian or perturbative results, combining also results from different approximation methods. And in the waveform modes, one also tries to do a similar thing. And one usually factorizes the waveform modes into pieces. And there's a good way to motivate why one does it. But it's not unique. So it's a bit of an art also, right? One tries some resummation, one checks against numerical relativity. And if it works, then one uses it, one works with it. But there are also some pieces which are not so nice in the modes, let's say, or which one would like to understand better how to model from more first principles, because most analytic results for the modes in the literature are only for circular orbits. But towards the end of the in-spiral, the motion becomes more and more non-circular. So also there, it's important to go beyond the circular motion and to eccentric orbits to make the model better.
Great. Next question.
Thanks for the great introduction to EOB. I wanted to ask about if you could say something about the future. Like there was a recent paper from Pure and Haster that said that numerical relativity is going to need an order of magnitude more for next generation gravitational wave detectors, and analytic waves are going to need 3 orders of magnitude more. So can you say something about what kind of things are in store to do that?
Yeah, so that was about numerical simulations or
well, the paper talked about both. It talked about both the numerical relativity, and it said you need even more orders of magnitude of improvement for the analytic models like EOB.
Right. Yeah. Okay, now I remember. Yes. Yeah. So that is true. Well, I mean, there's still many things so many post-Newtonian results that are not yet incorporated. So into the model. So one should do that. But also, in particular, when looking at the waveform and waveform modes for spinning bodies, many things haven't been computed yet. I mean, I don't quite recall what the current status is, but I think for the generic waveform, for quite a long time, it was only second post-Newtonian order. And now people are starting to move also to higher orders there. But yeah, it needs some manpower to compute these analytic results and also to cross-check them between different groups. That is very important because these are long computations, which nowadays are often done with Feynman integrals, etc. So, and yeah, there are many places where things can go wrong. Yeah, but there are many advancements in doing these analytic computations. So there's a lot of room to actually get better results. Yeah, it's just one needs to do it.
Yeah. Okay, Gustav, maybe next.
Thanks for a really nice talk, Jan. So we know that there are a lot of different ways that we can map gauge invariant observables between bound and unbound type orbits.
Yeah.
Do you think at some point it may be possible to get to an EOB style waveform without having to go through the mechanics of constructing these Hamiltonians along the way? Do you think there's a more direct route, as it were?
Yeah, I would. That would be very interesting, because one thing that makes this a bit messy is that all the quantities one works with are gauge dependent, coordinate dependent, and that's not very nice. In particular, because the gauge choice, it kind of matters here, because it's a resummation, right? So if you go from one post-Newtonian gauge to another, but then you do the resummation and take it as exact, you get different results. So it would be nice to work with gauge invariant blocks, like say scattering amplitudes, right? So if you could say you encode, yeah, I don't know how to, how to do it. So that's the question to get rid of Hamiltonians and stuff.
I have one other question actually, which is you mentioned that PM is likely to be much better for the more eccentric types of orbits.
Yeah.
Can you comment on how likely it is that we actually in the real world end up detecting a binary for which, you know, this actually starts to matter?
Yeah, so I believe this was partly answered by Ilya Mandel, right? So I mean, definitely people will want to work with eccentric waveform models, right? And detecting actual scattering, maybe it's not so likely, but maybe also not completely excluded. But I mean, eccentric waveform models, I would think at some point in the future they will be detected, particularly with LISA. Yeah.
Thanks.
Right, there was a question behind there.
Hello. So you mentioned that PM can be used to find better resummations of conservative dynamics of post-Newtonian approach.
Yeah.
But you also mentioned earlier that to create a waveform, it is not enough to have conservative dynamics. You also need the multiple moments. So
yeah.
Can you comment on how one can use the PM Hamiltonian to get expressions for the multiple moments? Yeah.
Yeah, you mean a waveform for post-Minkowskian, or?
Well, no. Let's say you have a PM approach and you create an effective Hamiltonian.
Yeah.
But unfortunately, unlike the PN case, you do not know the expressions for the multiple moments in terms of the coordinates, like the integrals over distribution. Yeah. So, is there a way to get that from the PM approach as well?
Actually, I don't know. I mean, naively, one would say that the whole expansion of a waveform into modes is not guaranteed to be good for post-Minkowskian scattering, at least not in the high energy regime, because all multiple moments of the radiation might contribute in a similar amount. So that's maybe the first thing to question. But I think Gustav will maybe talk a bit more about post-Minkowskian waveforms. So there, usually you compute the full waveform in one piece without the decomposition into modes, which is maybe also something interesting, right? So in some sense, you resum all the modes of the waveform. So yeah, maybe this is a way to use that. I don't know.
Right. I was actually thinking of bound systems, but you use PM to get a resummed Hamiltonian kind of thing. But now you want a waveform for the bound system, but using PM results. And so far, I don't think there has been any work on that, right?
I don't think so, no.
Okay, so as Gustav says, we need a gauge invariant way to get.
All right, we're out of time, so let's thank Jan again.